Okay, guys, Miss Amberton started making an announcement, so I went ahead and stopped the video so that I could listen to the announcement and just about some things that teachers are going to have to do over the next week or two. And there was one more little thing that I wanted to cover with you on this video. Again, remember that this video and the previous one that I just did, I'm going to be naming them Ideal and Combined Gas Laws 1 and 2. Are for Tuesday and Wednesday. So I will put one Google form that will cover both the ideal gas law and combined gas laws. There is another page in your packet over that has both ideal gas law and combined gas law problems on it, so I wanted to look at a few of those as well. Again, these are all example problems. The last video was kind of long, and this video, I'm going to do maybe 4 example problems. You don't have to watch every single example problem that I do. I just want to make sure that I'm doing plenty so that if you have questions, you can go through and look. But if you only need 1 or 2 examples and you know what you're doing, then you don't have to watch the rest of it. Just go do the Google form, the Google assignment that I posted. But I'm making, I'm doing several example problems in case you have a question, in case you need extra help with doing these. So again, the ideal gas law is PV NERT, PV equals nRT, and then the combined gas law, P1V1 over T1 equals P2V2 over T2. So what we're going to do is we're going to read the problem and decide which one of those do we need to use. Number 1, if 4 moles of a gas at a pressure of 5.4 atmospheres have a volume of 120 liters, what is the temperature? So here we're given a pressure of 5.4 atmospheres, so we know that's a P. We're given a volume of 120 liters, we know that's a V. And we want to know what the temperature is, so we know that's a T. The other thing that we're given here is 4, and let's just go ahead and say that it's 4.0 moles. Well, only one of these two equations uses moles, which is N. That is our ideal gas law, so this is N. And then it's asking us for temperature, which is T. So we're going to substitute our numbers in. PV equals nRT. And again, notice what we do every time we have a problem is we identify what we're given, what variables those are, we identify what we're being asked for, and then we determine the correct equation to use and we substitute the numbers into the equation. So our pressure, 5.4 atmospheres. Our volume, 120 liters. Our N, 4.0 moles. Okay, our R. Remember, we have 2 R's, and we'll go back here and look at those again. One R is 0.0821 liter atmosphere mole Kelvin. The other one is 8.314 liter kilopascal mole Kelvin. Okay, well, notice here our pressure unit is atmospheres. So this means we're going to have to use the 0.0821 liter atmosphere mole Kelvin for our R. So 0.0821 liter atmosphere mole Kelvin. And then our T is what we are solving for. So again, I'm going to multiply these out first. So on the left, 5.4 times 120 gives me 648, and that is liters and atmospheres. On the right, 4.0 times 0.0821 equals, and that gives me 0.3284. Moles cancel out, and what I have left is liter over atmosphere, or liter times atmosphere over Kelvin times T. Okay, so to solve for T, I have to divide both sides by 0.3284 liter atmosphere over Kelvin. Liter atmosphere over Kelvin cancel out. All of this cancels out on this side, and on this side we have 0.3284 liter atmosphere over Kelvin. Again, liter atmosphere cancels out, and we're left with Kelvin. So we're going to do 648 divided by 0.3284. And we get T is equal to 1973.20341, and of course our unit that isn't canceled out is Kelvin. We look at our problem and it looks like we have 2 significant digits. 4.0 has 2 significant digits, 5.4 has 2, and 120 also has 2. So to round this to 2 significant digits, we're probably going to have to put this in scientific notation. 1 9, the 7 makes the 9 go up, which makes that a 2. So if we just said 2,000, that would only be one significant digit, so we're going to put 2.0 times 10 to the third, because again, we move that decimal 1, 2, 3 places to the left. 1.97 rounds to 2.0 times 10 to the third Kelvin, and that is our temperature. So if we have this over 5 times the normal pressure on something, a huge volume of 120 liters, and 4 moles of the gas, it looks like the temperature is almost 2,000 degrees Kelvin. Okay, number 2, if I initially have a gas with a pressure of 84 kilopascals, a temperature of 35 degrees Celsius, I heat it an additional 230 degrees, what will the new pressure be? Assume the volume of the container is constant. Notice here, I'm talking about 2 temperatures and 2 pressures. I'm not talking about moles of gas. It isn't asking me for moles of gas. It isn't giving me moles of gas. So if it doesn't say anything about moles of gas or amount of gas, then I'm probably not using the ideal gas law because that involves moles of gas. The combined gas law does not. So I'm probably using P1 B1 over T1 equals P2 B2 over T2. Again, notice the volume remains constant, so I can just get rid of volume. And what I have left is P1 over T1 equals P2 over T2. So if I have a gas with a pressure of 84 kilopascals, that is a pressure, and a temperature of 35 degrees Celsius. So again, the gas has this pressure and this temperature, so we're going to call this P1 and T1. Those go together because at this pressure it has this temperature. I'm going to heat it an additional 230 degrees, and you guys, that is going to be degrees Celsius. What will the new pressure be? So I'm solving for P2. Now, if I heated an additional 230 degrees and I started out at 35 degrees Celsius, then this means that this temperature is 35 plus 230, or 265 degrees Celsius. Okay, so now before we start substituting numbers in, we know we have to have our temperature in degrees Kelvin. So 35 plus 273 is 308 K. And then 265 plus 273 is 538 K. So our P1 then is 84 kilopascals. Our T1 is 308 K. Our P2 is what we're solving for. And our T2 is 538 K. So to solve this, you can do the cross multiplying, or I can see that I'm going to have to multiply both sides by 538 K to get the P2 by itself. These cancel out, K cancels out, and so P2 is going to be equal to 84 times 538 equals divided by 308. And I'm getting 146.727272, so on and so forth. And my unit is going to be kPAs, or kilopascals. Again, looking at significant digits, 84 has 2, 35 has 2, and 230 has 2, so I'm going to round this to 2 significant digits. So the 6 makes the 4 a 5, that will be 150. And again, my unit is kPAs, or kilopascals, because my P1 was given in kilopascals. That means my P2 is also in kilopascals. Okay, a couple of other problems to look at here. My car has an internal volume of 2,600 liters. If the sun heats my car from a temperature of 20 degrees Celsius to a temperature of 55 degrees Celsius, what will the pressure inside my car be? Assume the pressure was initially 760 millimeters of mercury. Okay, so I have an internal volume of 2,600 liters, which is a V. I have a temperature of 20 to begin with, and then a new temperature of 55. And I want to know what the new pressure will be. Okay? So my car has an internal volume of 2,600 liters. So here's my question. The volume is 2,600 liters. Does the volume of your car change when it heats up from 20 to 55? No, it doesn't. So pretty much this is a constant. The volume of your car, 2,600 liters, doesn't change no matter really no matter how hot you get it. If you heat it from 20 degrees Celsius to 55 degrees Celsius, the volume of your car is still the same. So therefore, V is constant. We have T's here, and we're looking for the final P if the initial P was 760. So again, we have no mention of moles here, so we're probably not using the ideal gas law. We're going to need to use the combined gas law. P1, V1, T1 equals P2, V2 over T2. Okay, as we just said, the volume of your car is 2,600 liters. The volume of your car doesn't change even when it heats up. And so therefore, the volume of the car is going to be constant. So we're going to go ahead and get rid of the volume here and substitute in what we have left. So P, it looks like here our pressure was initially 760 millimeters of mercury, and we want to know what will the pressure inside the car be when you heat up the gas inside. So that's going to be P2. Obviously, the temperature initially was T1, and then the final temperature is warmer. We've heated it up to 55, so that's T2. Now, before we can start substituting numbers in, we are going to need to convert those Celsius temperatures to Kelvin. So T1 is 20 degrees plus 273, which gives me 293 K. T2 is 55 degrees plus 273. 55 plus 273 equals 328. Okay, so now we can substitute our numbers in. P1, 760 millimeters of mercury. T1, 293 K. P2, we don't know. And T2, 328 K. Again, we're solving for P2. We can see here we're going to have to multiply both sides by 328 K. Cancel out, the 328s cancel out. On the right we have P2, on the left we have 760 times 328 equals, divided by 293 equals, and then we get 850.784989, and this is, in this case, millimeters of mercury. Since our initial pressure was in millimeters of mercury, that is what our final pressure will be as well. Looking at our significant digits, 2600 has 2, 20 has only 1, so I'm going to put a decimal there just so it'll have 2, because I don't really want to do one significant digit in my answer. And 55 has 2 and 760 has 2. So we're going to round this to 2 significant digits. So that will be the 8 to 5. The 0 doesn't change the 8 and the 5. So 850 millimeters of mercury would be my answer for P2. All right. Check that and make sure that makes sense. If I raise the temperature, should the pressure go from 760 to 850? Should it increase? And yes, it should. Remember, there's a direct relationship between pressure and temperature. The higher the temperature, the faster the particles are moving, the more they're going to collide with the walls of the container and create more pressure. So higher temperatures do mean higher pressures. So that makes sense. Number 4 relates back to number 3. How many moles of gas are in my car in problem number 3? Okay, moles of gas. Well, that tells me I'm going to have to use the equation with moles, which is PV equals nRT. Okay, so then how do I do this? Because I have 2 pressures and I have 2 temperatures. Again, my volume remains constant, so I know that V is going to be the 2600. When you're doing this for this problem, just make sure you use either the initial pressure and temperature or the final pressure and temperature. Either one should give you the same answer. And if you don't believe me, you can try it with both of them and see, and you should get about the same answer whether you're using P1 and T1 or whether you use P2 and that you calculated and V2. So, or I'm sorry, P2 and T2. So we're just going to go ahead and we'll just go with the ones that they gave us. We'll go with the volume, which remained constant, that they gave us of 2,600 liters. We'll go with the T1, which we said was 293 K, and we'll go with the P1, which it told us was 760 millimeters of mercury. Now, so let's go ahead and plug in. Now we have pressure. We're going to go with P1, which is 760 millimeters of mercury. Well, we don't have a gas constant. We don't have an R that has millimeters of mercury. So we're either going to have to find a new gas constant, which I'm sure you can find one that has millimeters of mercury in it, or what we can do is we can say, okay, we can convert millimeters of mercury to atmospheres. And something that we know, or you're going to know here in just a minute, I've told you this before, but you probably don't remember it, 760 millimeters of mercury is 1 atmosphere. So since the pressure is 760 millimeters of mercury, then 760 millimeters of mercury is 1 atmosphere. So P in atmospheres is 1. Again, that is something that you know. You can look that up to see the relationship between millimeters of mercury and atmospheres, or you know because I told you that 760 millimeters of mercury is 1 atmosphere. Remember again, atmospheric pressure, which is the pressure we're under right now, is 1 atmosphere, 760 millimeters of mercury, and 760 torr. All 3 of those are 1 atmosphere. Or they're all, I should say, equal to one another. And I'm not sure what atmospheric pressure is in kilopascals. I think it's 101.3 or something like that. I think that's right. Okay, so all of those are the same amount. So if I have 760 millimeters of mercury, that is 1 atmosphere. And again, I had to change that to atmospheres because my gas constant that I have, I either need atmospheres or kilopascals. Those are the only 2 gas constants that I have given you. I'm sure there are others, but those are the 2 that I've given you. Okay, so that's why I changed it to atmospheres. That makes it easier. Okay, V, again, we're using P1. P1 is 1 atmosphere. V1, or any V, is 2600 because the volume of your car remained constant. N is what we're solving for. We don't know what it is. It's what it's asking us for. R, again, since we're using atmospheres here, we're going to use our R in atmospheres. So it's 0.0821 liter atmosphere mole Kelvin. 0.0821 liter atmosphere mole Kelvin. And then we're going to use our T1. And our T1 we said was 293. Okay, so our Kelvin cancels out, and we can see on the left we have 1 atmosphere times 2,600 liters, which is 2,600 liter atmosphere. On the right we have 0.0821 times 293, which is 24.0553, and that is liter atmosphere over mole because Kelvin canceled out, and that is times N. So to solve this, we have to divide both sides by 24.0553 liter atmosphere over mole. And everything cancels out on the right, and all we have left is N. On the left, the liter atmosphere cancels out, and what we have left is mole, which is what we're solving for. So 2,600 divided by 24.0553 equals, and I got 108.084281, and that is moles. And again, looking at it looks like we need 2 significant digits. So that'll be the 1 and the O. The 8 rounds the O up to a 1, so that's 110 moles. So in your car, if you have it at a temperature of 20 degrees Celsius or 293 K, if the volume of your car is 2,600 liters and the pressure is 1 atmosphere, which is atmospheric pressure, then you have about 110 moles of gas in your car. Okay, and again, if you decided to use P2, which we calculated to be 850 millimeters of mercury, you would have to convert that to atmospheres by, again, you could set it up as a stoichiometry problem, 850 millimeters of mercury over 1, 760 millimeters of mercury in 1 atmosphere. To cancel out the millimeters of mercury, so 850 divided by 760 gives you 1.118421053, and I'm not rounding that because that's not a final answer, so that would be my pressure, P2, so I could plug it in there. Again, my V is 2,600. My N is what I'm solving for. My R would still be the 0.0821 because I'm using atmospheres for my pressure, and then the T would be my T2. So if you wanted to use P2 and T2, if you want to try those and plug those in, you should still get around 110 moles. As long as you're using this, either all the initials or all the finals, you would get the same answer. You couldn't use an initial temperature and a final volume, or a final pressure, I should say. You have to use initial temperature, initial pressure, or use final volume, final pressure, final temperature. Okay, I hope that does it for you. Please email me if you have any questions, and we'll try to work it out. I'm going to be, you should have a Google assignment posted that you need to have done and submitted to me by this Friday evening at 11:55 p.m. And we'll talk to you later.